In mathematics, differential calculus is a subfield of calculus concerned with the study of the rates at which quantities change. It is one of the two traditional divisions of calculus, the other being integral calculus, the study of the area beneath a curve. The concept of a derivative in the sense of a tangent line is a very old one, familiar to Greek geometers such as Euclid, 300 BC, Archimedes, 287 to 212 BC, and Apollonius of Perga, 262 to 190 BC. Archimedes also introduced the use of infinitesimals, although these were primarily used to study areas and volumes rather than derivatives and tangents. The modern development of calculus is usually credited to Isaac Newton, 1643 to 1727, and Gottfried Wilhelm Leibniz, 1646 to 1716, who provided independent and unified approaches to differentiation and derivatives. The key insight, however, that earned them this credit, was the fundamental theorem of calculus relating differentiation and integration. This rendered obsolete most previous methods for computing areas and volumes. For their ideas on derivatives, both Newton and Leibniz built on significant earlier work by mathematicians such as Pierre de Fermat, 1607 to 1665, Isaac Barrow, 1630 to 1677, René Descartes, 1596 to 1650, Christian Huygens, 1629 to 1695. Blaise Pascal, 1623 to 1662, and John Wallis, 1616 to 1703. Regarding Fermat's influence, Newton once wrote in a letter that I had the hint of this method of flux ions from Fermat's way of drawing tangents, and by applying it to abstract equations, directly and invertedly, I made it general. Isaac Barrow is generally given credit for the early development of the derivative. Nevertheless, Newton and Leibniz remain key figures in the history of differentiation, not least because Newton was the first to apply differentiation to theoretical physics, while Leibniz systematically developed much of the notation still used today. Since the 17th century, many mathematicians have contributed to the theory of differentiation. In the 19th century, calculus was put on a much more rigorous footing by mathematicians such as Augustin Louis Cauchy, 1789 to 1857, Bernhard Riemann, 1826 to 1866, and Karl Weierstrass, 1815 to 1897. It was also during this period that the differentiation was generalized to Euclidean space and the complex plane. The primary objects of study in differential calculus are the derivative of a function, related notions such as the differential, and their applications. The derivative of a function at a chosen input value describes the rate of change of the function near that input value. The process of finding a derivative is called differentiation. Geometrically, the derivative at a point is the slope of the tangent line to the graph of the function at that point, provided that the derivative exists and is defined at that point. For a real-valued function of a single real variable, the derivative of a function at a point generally determines the best linear approximation to the function at that point. Differential calculus and integral calculus are connected by the fundamental theorem of calculus, which states that differentiation is the reverse process to integration. Differentiation has applications to nearly all quantitative disciplines. For example, in physics, the derivative of the displacement of a moving body with respect to time is the velocity of the body, and the derivative of velocity with respect to time is acceleration. The derivative of the momentum of a body with respect to time equals the force applied to the body. Rearranging this derivative statement leads to the famous F equals ma equation associated with Newton's second law of motion. The reaction rate of a chemical reaction is a derivative. In operations research, derivatives determine the most efficient ways to transport materials and design factories. Derivatives are frequently used to find the maxima and minima of a function. Equations involving derivatives are called differential equations and are fundamental in describing natural phenomena. Derivatives and their generalizations appear in many fields of mathematics, such as complex analysis, functional analysis, differential geometry, measure theory, and abstract algebra. What is the purpose of differentiation? Differentiation and integration considered by all scientists throughout the ages as one of the best sciences that guided the mind of man over all times. The fields of the use of calculus are very wide. It enters into many fields and are not limited to specific people or to those who use it only, but to almost all human beings. Here are some examples of its benefits. Number 1. Cars. A car doesn't leave from the factory without knowing where the center of its mass, weight, and central axis are. This helps to determine the factors of security and safety on different roads and different speeds of the car. This is done only by calculus. Number 2. Design. The graphic engineer uses calculus to determine the difference and change of three-dimensional models and how it will change when exposed to multiple conditions. This helps him to create a very realistic environment in 3D movies or video games. In games like the Need for Speed or GTA, all the statistics that the player sees during the race on the screen include the speed of the car and the distance between him and the contestants and the time between his car and each car of the participants in the race in the second and tenth of the second. These calculations of differentiation and integration are done in the moment while enjoying the game. This principle applies to many games. Number 3. Space. Space engineers often use calculus when planning long missions to launch a probe because they need different speeds in the probe's orbit proportional to gravity and altitude. Calculus helps them to determine all these variables with infinite accuracy. Calculus does have a lot of practical uses that you probably won't comprehend at first. The most common practical use of calculus is when plotting graphs of certain formulae or functions. Using methods such as the first derivative and the second derivative, a graph and its dimensions can be accurately estimated. These two derivatives are used to predict how a graph may look like, the direction that it is taking on a specific point, the shape of the graph at a specific point, if concave or convex, just to name a few. In fact, you can use calculus in a lot of ways and applications. Among the disciplines that utilize calculus include physics, engineering, economics, statistics, and medicine. It is used to create mathematical models in order to arrive into an optimal solution. For example, in physics, calculus is used in a lot of its concepts. Among the physical concepts that use concepts of calculus include motion, electricity, heat, light, harmonics, acoustics, astronomy, and dynamics. In fact, even advanced physics concepts including electromagnetism and Einstein's theory of relativity use calculus. In the field of chemistry, calculus can be used to predict functions such as reaction rates and radioactive decay. Meanwhile, in biology, it is utilized to formulate rates such as birth and death rates. In economics, calculus is used to compute marginal cost and marginal revenue, enabling economists to predict maximum profit in a specific setting. In addition, it is used to check answers for different mathematical disciplines such as statistics, analytical geometry, and algebra. As you can see, calculus has a huge role in the real world. For most professions, learning it is the key to success. So this is why you can't dismiss calculus as just another nuisance. If it is, interest on the matter wouldn't have lasted as long as it did. Let me pass you a quote given by a great physicist, engineer, and inventor. "The day science begins to study non-physical phenomena, it will make more progress in one decade than in all the previous centuries of its existence." Nikola Tesla. Basically, calculus is used in every single thing in our day.